send it out there. How weird is that? Normally, I don't have to go through and admit everybody one at a time, but whatever. I'll do what it takes. Okay. Got to get rid of this. Come on, get out of there. And we'll get rid of that. And we need to get rid of this. Okay. Back to this. Carboxylic acids. Long alkane chain with a carboxylic acid on the end. C double bound O, that's a carbonyl, carbon and oxygen, bound to a hydroxyl. So RCO, OH. How do we name them? We count the carbons. We count those carbons up, and we add oic acid. It's just that easy. And this is weird. People just keep signing in and signing out. Odd. Eugene, are you doing this? Because you got the look of a crazy hacker. You know, I'm just thinking if any of you guys are doing it, it's either you or Anissa. I don't know who. All right. So let's do the counting here. 1 is methyl, but it's meth, not ane, methanoic acid. 1, 2, ethanoic acid. You could also say ethyl carboxylic acid, but no one bothers to. 1, 2, 3, methyl, ethyl. What's 3? Is 3 wethyl? Help me out here. Is 3 wethyl?
Propyl.
Really? That sounds way better. Okay, I'll go propyl. Methyl, ethyl, propyl. Methanoic acid. 1, 2, 3, 4. Methyl, ethyl, wethyl, butyl. Butanoic acid. Easy to name. Lots of biological functions, obviously, in the phospholipid bilayer and the fluid mosaic model of cells. Benzene. Benzene is a cyclic compound. It looks like cyclohexane, 1, 2, 3, 4, 5, 6, except it shares electrons. Because of this, if you're analyzing something and benzene is present, you'll have a bunch of shared electrons whipping around, and it will show up on a UV spec as very, very, very bright. Just got to check here. Various signing ins going. Very strange. All right. So they share electrons. We call that their resonance stabilized. Their stability is literally dependent on everything in that cyclo ring sharing electrons continuously, which gives it slightly different properties and, in fact, makes it rather unique. How do we drop it? How do we draw it? We draw, ready? Carlo, the stop sign. It's a stop sign with an unfinished smiley face. Do you know why it's not smiling? Because this is organic chemistry. Ouch. So benzene can also be used for certain European automobiles as a hood ornament. That would be Mercedes benzene. Drum roll. Andrew, hit it. Okay, thanks. So this circle isn't just a happy face. It is a representation of unshared electrons that are whipping around. And at any given time, they're being shared between all the carbons on the corners of this molecule. So benzene is stable because it's resonance stabilized. It is, just by its existence, is sharing electrons. The reason I want to draw separate attention to this is because there's only two basic ways of naming benzene compounds. How does it work? Real easy. If the benzene is the parent, that is, if the benzene is the most important compound there, right? That's the parent. And we'd say it's benzene something or benzyl something. Yeah, here I did one right here for you. It looks like isopropyl, benzene. There it is in red. Now, here's the catch. If you have a functional group, a higher priority group on this attachment, that becomes the parent immediately. In organic chemistry, whoever has the most important stuff is the parent chain. And that happens here as well. So here we've got this benzene minding its own business, sharing electrons, but attached to it we have 1,2 methyl ethyl ethanol. Well, that means now ethanol is the parent, and the phenyl group, we use the prefix phenyl to indicate benzene is attached. In this case, It's attached 1 carbon, 2 carbons. So we say on the number 2 carbon, it's a 2-phenylethanol. When you see the word benzene, it means it's the parent compound and the higher priority. If you see the word phenyl something, it means you have a benzene attached to something, and that something, in terms of its chemistry, is more important, usually, typically, greater electron density. You okay with that? Benzene's the most important group. It's something benzene. If the attached group, if the R group has a greater importance. Dr. Henderson, are you yawning? Goodness gracious, I know. I can smell a yawn miles away. It's too bad we're not in a lecture theater because I can do it when I'm not looking, which begins to freak people out. If you have something with a higher density, a greater functional group like ethanol, there's our electron density, this is the parent. So this is ethanol, but we need to say phenylethanol, and it's attached to the 2 carbon. Just to rehash, which seemed to make you pretty freaked out last time we tried this a few weeks ago, I just want to run through the naming attachments. Just going to say this again. It is so much easier for you to learn these basic things than try to stumble it all together at the last minute in a test. That's really tough. All right. RCO OH is a carboxylic acid. And we always say the name, parent name, for example, ethene, ethyl, ethanoic acid. Esters are always RCO OR. Yeah, Andrew, I said I was going to name things like a 17-year-old girl from Malibu, California, hanging out on the beach. Long story I could tell you there, but I'm not going to. RCO-OR. And we say OH or anoate, depending on what it ends in. Ketones, RCO-R. And we add the word one or anone. Aldehydes, RCO-H. And we add we add al to the end. And I've also seen people write out the whole word aldehyde. That's okay, but it makes for a pretty long name pretty quick. So most folks will just tack on 2 letters, Al. Alcohols, ROH. You can add all. It might be anol. Both are correct. I usually try to keep it as short as possible. Just add, OL. ROR is ethers. How do I remember that? Anybody here from Africa? Lions roar, ROR. Yeah, so, getting into my head on how I actually remember these is probably not a healthy experience. So hopefully you've got a better system in place. Excuse me. Alkynes, 1, 2, 3. 3 bonds. That means these carbons only need 1 other bond each. They are ines. This is unsaturated because it's as many bonds to carbons as you can get. If there's an otherwise neutral carbon chain, that'll be the first site of attack because 3 times the bonds is 3 times the electronegativity. So it isn't just functional groups that are a site of attack. The extra bonds are also a functional group and a site of attack as well. Alkenes, whole bonds end in -ene. Alkanes end in -ane. Amines are, how do I say it? NH2 or NR3. Amides have the RCO, the carbonyl structure. Nitriles, or the family of cyanates, are deadly poison, competing with hemoglobin for your oxygen. And finally, when you're going to have side chains, you add not just methane, you'd say methyl, ethyl, etc. for your various side chains. And we're going to see lots of examples of this stuff as we plow through the material. But again, I've covered this before. I'm going to keep covering it because I learned from my sons when they were young that nagging is a very good instructional technique. Can I demonstrate what I learned from my sons? Can we play PlayStation? Can we play PlayStation? Can we play PlayStation? Can we play PlayStation? Oh, for God's sakes, play PlayStation. So I'm going to keep nagging organic chemistry like that. And hopefully you'll learn organic and not PlayStation. What's that? Oh, okay, fine. Additional tidbits of information. R groups mean some attached carbon or organic group. It simply means something's attached. But for our purposes, it doesn't really matter. We're just saying this doesn't fly off magically into the air. It's attached to something. So it's very common to use R or an R group as describing attached to some other alkyl, that is carbon-containing group. So get used to it. You're going to see it. Not everybody's going to want to draw complete structures all of the time. After a while, it gets to be a drag. Now, alkanes, absolutely the simplest carbon chains. Generally, by the way, how many bonds does carbon like? Is it 7?
4.
Is it 1.1?
4.
4?
4.
I was going to say clouds. You guys are way better than this. Okay, 4. How many bonds does nitrogen like?
3.
3.
Oxygen?
2.
2.
Hydrogen?
1.
1.
And what about the most delicious element, polonium?
What?
Fine. Tough crowd today. Okay. So they're generally unreactive. They've got their 4 bonds. Everything's cool. Typically, you can react most things with anything that disturbs their equilibrium. Strong acids and bases, oxidizing agents, etc. Typically, alkanes and cycloalkanes are inert enough that they're not really bothered. Short version of organic is this. If you want to be crazy enough, you can get anything to react. For example, you could use something called a bomb calorimeter, which should tell you how safe it is, which heats things up under enormous pressure with tons of acid. Yeah, you're going to get it to react. But that isn't typically how we go about our business in organic chemistry. So generally, alkanes are about as neutral as you're going to get. What they can do, diagram, they can undergo combustion. Now, do any of you like fires? No, Holly, I don't mean your church burning weirdness. I'm talking about, like in the backyard with marshmallows or perhaps wieners. What do people throw on?
Yes.
Yeah, okay, fine. Yeah, it's going to be warm tonight. Thinking of a fire, by the way. All right. Humans understand combustion. We've done burning probably for close to 100,000 years. Carbon-containing molecules burn well. They burn steady. They burn evenly. So although we can't do what I would call the classic organic reactions for carbon compounds without a lot of acid, base, heat, etc., they're more than willing to undergo combustion, which is why your car runs on some form of alkane chains, gasoline, 80 octane, 80 carbons long. So those numbers are actually related to what you're paying for in terms of the carbons. Just saying. Okay. Stereochemistry. Everybody hates this, but I thought I put it in anyway. Usually people at this point are going to ask me a question about Bluetooth, earbuds. Yeah, go nuts. No? You're going to behave? Okay, good. Stereochemistry means, ready? Molecules have specific shapes. And just like proteins and enzymes, particular shapes change how they might behave. Not always, but it could change how they behave, and it may certainly change the information you get in the instrument lab. That's important. You might have what you think is exactly the same compound for 6 of your 7 tests, and one of the tests says, no, it isn't. So it gets tricky. I do know that at the end of one of your instrument courses, you do an advanced instrumentation, you're given 10 unknowns, and you've got the term to figure them out. What you soon realize is that some of the tests you will do will give you conflicting information. It's not a perfect world. Not everything gives you an exact answer. So you have to be aware that many chemicals will exist in more than one form. So chirality, stereoisomers. Okay, you got a hand? Who's got a hand? Let's see your hands. Anissa, you're going to fail you for no hands. Beckett, I've already failed you. Doesn't matter. Dr. Gap, no hands? Wow. And look, Havoc, you're playing on your phone? Good God. Basically, if you hold up your hand to the mirror, it is the same object, but it doesn't really superimpose like this, right? See this? Do that? Spider on a mirror? There's your superimposable. If they're both going the same way in like that, they cannot be superimposed over each other. And we call those And the reason I'm telling you, I'm not going to go in a lot of depth, but you're going to hear about this later in instruments. So I figured I'd break the news to you. Chiral objects are not superimposable, and they will be a bit of an annoyance when you do your instrument labs with them. So just be aware of it. The numbers you're going to get are going to happen for a reason. This is going to be one of the reasons. Enantiomers are when they look the same, but they don't technically superimpose. For example, in this diagram I have here, the R groups are pointing out at you. And when you go to superimpose them, basically the thumbs are pointing in the wrong directions. They do not superimpose properly. And when you go to analyze them by HPLC, when you look at volatiles, sometimes when you're doing electron capture with gas chromatography, these are going to give you wonky results. Once you're aware and you're looking for them, it's easy. But you need to know that a pure chemical may exist in more than one form. And that's an important piece. Everybody assumes it's 100% this. Yeah, but 100% this may be waffling between sort of two different structures, flickering between these structures all the time. And it does not come with a handy label that says, warning, maybe flickering between structures. So you need to be aware of that. Is that okay, Dr. Francis? I might be lying, I'm too lazy, too much effort. Okay. Now, reaction basics. This stuff does count. The stereochemistry and enantiomers you're going to talk about later in your instruments. The reaction basics, let's talk about it now. I spoke about this earlier. I apologize if I'm going through it and you know it flawlessly, but you have to have this. We refer to any negative entity as a nucleophile. As a professor, as your instructor, you would say Blick is a nucleophile, a negative entity. In fact, you probably have better words than that. My last name, Blick, rhymes with a lot of stuff, so I'm pretty well versed in this kind of thing. Any negative entity that will be attracted to a positive part of a molecule. We refer to them as a Lewis base. They act like a base. They are able to and will bind to protons and other positive entities. So a Lewis base, by definition, is a chemical structure that can grab onto protons and let them go, and the group of nucleophiles falls into that category. Typically in chemistry, we call them nucleophiles, though, and not bases. Most of them, the broad range of them, are anions, negatively charged ions. And they are almost all involved in the classic reaction, nucleophilic substitution. A big negative nucleophile, boop, 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 comes in and knocks out something that's weaker. I know, it's like American politics all over again. It knocks out something that's weaker and takes over that space. The opposite, of course, are electrophiles, EP. That's any species with a positive charge that is attracted towards a negative center, right? We call those Lewis acids, just part of the basic chemistry concept. So nucleophiles, any negative component coming in to be involved in a reaction. Electrophiles, any positive component coming in to be involved in a reaction. How you doing there? We good? Oh, now it's too easy? Now you're bored? Wow, that's a tough group. 3 weeks ago, you had the look. Now you have the look. Organic is tough. Okay, let's go here. There's lots of reactions. I just want to cover the ones you're going to see over and over again. The simple, most common, happens all of the time, will happen against your will even, is substitution. Something with a bigger charge muscles its way in and bumps out something with a smaller charge. This happens all the time. One of the mysteries of organic chemistry is people think it's so hard to get a reaction to happen. Allow me to point out that is wildly untrue. It is super easy to get something to react. Don't cry, Dr. Francis. There's lots more to go. The hard part is getting the reaction to stop where you want and making a pure solution. Newsflash. Almost no reactions go to 100% completion. Almost no reactions are clean. For example, a 75% reaction rate where you make 75% of your target is considered a good reaction. 25% is something else. or unreacted materials. So if you're making injectable drugs, a lot of people resent 25% surprise in their medications. So, clean organic chemists get paid a lot. Elimination
Tumae!
is removing something. You walk into that molecule, there's a couple carbons, you pull out something, a hydrogen or something attached to it. The way it makes itself stable, it only has 3 bonds. How many bonds does carbon want?
Bigyan mo ng...
4. You know what it does? It forms another bond right away. Elimination, typically something leaves and it reaches stability by forming that double bond, period. I mean, the carbons are merciless. They're just like instructors. They don't care. Just don't. What they're going to do is reach stability. So if the easiest thing to do is to form another bond with an adjacent carbon, it'll do that. Addition, boom, adding something. A broad range of activities fall under this title. Alrighty. A couple examples here. Substitution. HCl, you've added a little hydrochloric acid to a mixture. You've got a, 1, 2, 3, and we've got a hydroxyl group. This is the negative bit, and chlorine is a giant negative bit. With no effort at all, it will bump off, push out the hydroxyl group, and here's the thing. Ready? What planet do we live on? Well, not me. I tend to go to various planets at various times. You guys are pretty much earthbound, right? What is Earth mostly covered with?
Water.
Water.
That's a good answer, but I was going to say organic chemistry, but I'm going to let you get away with it this time. Yes. In fact, anytime water can form, it will happen. That's the big secret of organic chemistry. No one seems to tell everybody. But the reality is water wants to form. Water forms easily on planet Earth. And so what they say is water is a good leaving group. Well, it's also a very easy to form group. So many, many, many reactions, you will see water as the byproduct. If you're designing a synthesis, if you can make a reaction where the waste product is water, you know what I'm going to say? Nice work. As opposed to cyanide or something toxic. So designing your reaction to make non-toxic is a big piece for me. I've taught environmental toxicology and environmental chemistry for universities for years. And there's a lot of reactions out there in industry that are not clean. Addition. Well, look here. This is a 1, 2, 3, 4, 5, a cyclohexyl group, but it's a cyclohexene. Well, when I look at that, I see a double bond. So that says to me, that's the area of electronegativity. It says to me, Rim, that that's where the reaction is going to happen. So if we're going to bump out this bond, these 2 carbons are going to be very unhappy. But if you have a large electronegative bromine ion, it will bind to those carbons, and that double bond is gone. You've added something, finished. How does it work? This has to be a big enough charge to be there. If it isn't, it will not work. Elimination. Here we have a cyclo alcohol. We're adding H2SO4 sulfuric acid. What are we going to do? We're going to have the sulfur solution bob away. You're probably making sulfur dioxide like acid rain. Dave says that's bad. Please don't make acid rain. I don't like that. But you're also making some water. And the residual, one of the OHs, is going to tack on to it's not going to tack on. You're going to make water and replace the missing bonds with the double bond alkene. I'm not going to do the rearrangements. I want you to get your brain around. These happen because of a larger charge group that has a greater affinity for an opposite charged area. If those conditions don't exist, you can mix these things together all day and nothing's going to happen. You can increase the collisions by adding heat. That helps. And sometimes we acidify to try to destabilize the bonds and add a lot of protons. But generally, you need to have an incoming group of sufficient electronegativity that it's actually going to get this to go. Okay. So substitutions. And I probably just said all of this at the cost of boring you. I'm going to have a little toast to myself. I'm feeling pretty proud about how boring I am. What do we have here? Chlorine, Cl2. Here we have a 3-dimensional, looks like a methane. What's going to happen? Well, in this case, it's been hit by light. HV means light energy. You guys know that? HV means light. And I got to tell you, this chlorine wants to be attached a lot more than a lowly proton. Remember, protons are very weak bonding. So it's going to come in, it's going to bind nice and tight and strong. And we've now got a chloromethane. What have we made left over? Hydrochloric acid. Oops. Easy peasy. Very often, you will find that these happen the easiest with charge groups like halogens or halides. That's the fluorine, chlorine, bromine, or iodine. And very often, if we're just talking about them generally, I mean, you could write the Cl, etc., but people refer to them as an X. So X, in this case, doesn't mark buried treasure. It marks out where there's one of these halogens / halides. Fluorine, chlorine, bromine, or iodine. And any alkyl halide, like up here, where you've added one of these X groups, we describe it as, ready, Rx, in red, in quotes. That's important. Here's a tip. It's in red. He probably means it. So alkyl halides, Rx, they're going to want to form. The desire of these electronegative chlorines to bond to this positive carbon is much, much higher than any hydrogen. So that'll happen very easily. And the result is an alkyl halide, or Rx. Okay, still good? Wait, Darlene, are you using Teddy as a pillow?
Yeah.
Because Teddies have rights, you know. Oh, man. Okay, I got to tell you the truth. I still have a teddy bear from 1963 that my great-grandmother from England gave me when she was 95. I still have it on my dresser. I mean, it's even muggier than I am, which is pretty scary. But the truth is, I still like that. Don't tell anybody. Okay, fine. Now, questions or thoughts? You good? Any group that leaves the reaction, right, gets displaced, is called a leaving group. I mean, in organic, it's literally as it sounds. The leaving group is the group that leaves the reaction. Water is a common leaving group. Okay.
Can I ask a question? Why didn't the chlorine replace two hydrogen? There are two chlorine molecules.
Because the carbon is a much more stable positive center. Again, hydrogens do have a positive charge, but it's nothing like this carbon proportionally. Where was it? Halogens and halide ions, and you might want to write this down especially. They're good leaving groups because they're weak bases. They can let go easily. Here's the part I didn't write down that you might want to. Good leaving groups, are you listening? Tend to be groups that are stable all by themselves. I can demonstrate. If all of us are at a big table and there's only 2 pieces of chocolate cake, there's going to be a whole lot of grabbing for that chocolate cake. Not a good situation. If all of us are at this giant table and there's 4,000 of pieces of cake, it doesn't matter if cake leaves. It's a sturdy leaving group. The reality is leaving groups tend to be fairly stable on their own. They're not put off. So halide ions, that great big strong negative charge, yes, it will bind to positive things, but left to itself, it's a stable, strong, powerful negative entity. Little tiny hydroxyl ions are also nucleophilic. They are negative, but compared to the great big powerful halogens and halides, they're not so good. They don't want to let go very easily. Therefore, to bump off an alkyl group, a hydroxyl group, you need a pretty good charge. So those substitution reactions are always going to happen when a bigger, tougher, more stable, stronger electronegative group comes in and displaces a weaker one. The weaker the base, the greater the reaction. That is, the greater the speed of the reaction, the greater the amount of reaction, that is completion, and the fewer leftover bits. For example, more reactive, fluorine, and as they become weaker ions, are less reactive. Now I want to compare 2 things for you. There are SN1 reactions and SN2. These are the fundamental 2 different types of substitutions. Brooke, did you finish your Slurpee? There's no way I'd know. I mean, you could say anything, right? How would I know? All right. SN2 means substitution, nucleophilic, and 2 means it's a bimolecular reaction. It involves two entities, two particles, if you will. Substitution, something bumping something out. It is nucleophilic, so it's telling you it's a strong negative group coming in right away. And it involves two separate molecular entities. What's going on? You are replacing something with something that wants to be there more. And in organic chemistry, that more is almost always going to be a stronger charge, a greater center of electronegative density, for example. A nucleophile, this Rx, alkyl halide, this is stronger, it'll bump that off. If it is not stronger negative charge, nothing's going to happen. So really, you can look up on the internet, or the Plagiarnet, I should say. You can look up in all sorts of textbooks, the CRC Chemistry Handbook. They will list the strength of these relative ions. Usually, these reactions, SN2s, involve colliding a nucleophile and the main or head carbon. Almost always, that's where it happens. It could happen other ways, but usually, most of the time, this is it. What happens? Ready? Here comes our nucleophile. Woo-hoo! You know what it's going to do? It's going to slam into here. And when it slams into here, this happy guy lets go. It's a happy, stable anion. It's a good leaving group. And instead of a hydrogen here, you've got the nucleophile. This slams into here. Now you've got a nucleophile there and the hydrogen there. You've replaced this guy with whatever that was. Two separate entities, this and that. Oh, Dr. Herring, look how happy you look. Nice. Good to see organic chemistry is as rewarding intellectually as ever. The SN1 occurs by you manipulating the conditions. It is a substitution. It is nucleophilic, but it involves one main component. It always goes through a little molecular entity. This is important, you guys. It's right here, called a carbocation. Now, it's not a cat for you cat lovers. It is a cation. It's a temporary existing case where a carbon only has 3 bonds and an unresolved positive charge. When the conditions are right and that forms, this carbon is going to grab onto something really quick because it wants, how many bonds does it want? 4. If it has 3, it's not happy. So we manipulate the conditions, the organic chemists, to create a carbocation, this positive charge. That's when the carbon has only 3 bonds and it wants 4. This happens, I'll explain it first, then I'll go through it. This happens very specifically in acidic environments. Let me explain. A carbon is in a chain. It's bound to a couple carbons. It's got a couple hydrogens. Well, here's the deal. Normally, it's not going to let go of a hydrogen. But if we put a bunch of acid, a bunch of protons in that liquid, there are literally trillions of protons very close by. At any given instant, some of those carbons are going to let go of the hydrogen they're bound to and grab onto another one. They have no allegiance. They will do this at a high enough concentration of protons. In that brief nanosecond where that carbon lets go and goes to grab the next one, it is a carbocation. It has a positive charge for that brief instant. So basically you can imagine that these carbocations are flickering on and off in an acidic environment. Again, for some reason you went to a bar filled with bikers, there's 100 beer on the table. Nobody cares if you grab one. If there's 3 beer and 4 biker, and Andrew, for some reason, you walk over and grab a beer off the table, someone's going to say something. In this case, in a sufficiently protic environment, that is one where you've made it acidic, and there's lots of protons, any carbon can let go and grab the next one. I mean, they're chemicals. They're not thinking organisms. And in that instant, when they let go, you temporarily make one of these, a positive carbocation. Here's the short version. If this exists and you have a nucleophile anywhere in it, it is going to slam into there. It's like a flashlight outside in the dark. it is incredibly obvious with respect to reactivity. So by creating a carbocation, by acidifying a mixture, you are causing an SN1 reaction. You're the driver. Let's take a look at what I wrote. So if we have a methyl carbocation, here's a tert, 1, 2, 3, 1, 2, 3, tert butyl. It almost always is in an acidic environment, and they are considered intermediate or transitory products. They're not permanent. They exist for an instant. However, if you have a good concentration of nucleophile in there, in that instant when they exist, when this carbocation exists, a nucleophile will slam into it, period. It is a function of that acidic environment that makes a carbocation. And you, my friends, as the organic chemist, can literally pour in H2SO4, HCl, add a bunch of protons, it'll go. And if you look at the textbooks or online, you'll discover that a whole lot of organic reactions, the first step is put acid in there for this very reason, to make it acidic, but moreover, to provide protons so you form a carbocation. Easy peasy reaction. Relative reactivity. Real easy rule of thumb. The stronger the charge, the more reactive. We've got a carboxylic acid. Yeah, it's polar. It's got a bit of a charge. Then we've got fluorine, hydroxyls, chlorine, bromine, iodine. Least reactive, most reactive. Short version. Bigger charge, bigger boom. We're not supposed to blow things up anymore. It's frowned upon. If I had been teaching basic lab skills, your first lab, Gerardo, I would have had you titrating vinegar into baking soda so you'd learn about wearing eye protection on the first day. I think that's a good lab. Yeah, they won't let me do that for some reason. Okay. Elimination. Elimination is as easy as can be. All you're doing is having a stable leaving group leave, and you're making up the missing bond by forming a double bond. Here's the thing. Something leaves, it's unhappy. Let's make a double bond. It's happy again. That's it. That's all. E1 means, ready? It went through the same carbocation. That means it was an acidic environment. And it eliminated because you made a carbocation, and that carbon wasn't happy. And since there wasn't a nucleophile it could grab onto, it simply made a double bond to the carbon next to it. An E2 reaction is bimolecular. You've got two things involved, two particles, two molecular entities. These tend to only happen when you're using stronger reagents, concentrated H2SO4, for example. You know, you've got to convince something to leave and set up the circumstances. So E2, that is bimolecular ones, typically involve a strong agent such as H2SO4. You'll notice the leaving group. Water, yet again. Virtually any reaction where there's a chance of water forming, it's going to form water. You're on Earth. It does it all the time. So let me go through this. The E2 reaction will always involve a strong base. Have any of you ever made soap or done saponification?
Yes.
Nobody here has ever gone out and killed a bear, or at least asked the bear for some bear fat, boiled it down with lye with strong base and made soap? Yeah, they used to make soap like that. It is truly horrible. No wonder people hate soap. All right. Typically, it is a strong base. Don't use lye. Use something nicer than that. And it has a group adjacent. For example, we've got some carbons. We've got a hydrogen here. And look here, we've got an alkyl halide. A strong element's coming in. It's going to pull this guy away, or this guy away. What happens? As these guys leave, a nice stable leaving group, the way it reaches stability is by a double bond. This is only going to happen under those strong conditions. So where you're using a weak acid, where the concentration is more dilute, it's really not going to happen. Where you will see this, and I'm telling you because you're probably going to see this in your advanced instruments, hint, 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 it happens on tertiary carbons, which just might be one of your unknowns next year. So when you start freaking out, try to remember this. So This occurs most commonly on tertiary carbons, carbons that are involved themselves bound to 3 other carbons. I've got a few examples here for you. The note you should take is right here. If you've got a primary carbon, it's the lowest rate of elimination, an E2. If you've got a tertiary carbon, more things attached, it goes a lot more easily. Basically, the carbon that has the most things attached will undergo the elimination more easily. And I have to give you a rule here that will also come back later. It's the Sate-Zeff's rule. The question is, if you happen to have this nice long alkene, and you've got 2 double bonds in it, it's a diene, which place are you going to have the reaction? The rule is, whatever has the most attachment is the one where you're going to get the substitution. That is, whichever has the greatest things attached to it, that's where your substitution or your elimination will occur. All right. Why? The more substituted, more parts attached, the better able to distribute charge with more things attached. And if it can distribute charge better, it's more stable. So lower stable things, easier to involve. High stability at the other end. Now, I wanted to talk a little bit today about competing reactions, because the simple truth is, although it'd be really wonderful if we put the stuff in the container and we thought, oh, it's just going to react. If that was our idea, that'd be great. The reality is carbon and other components need to have stability. They don't care how they get it. And that means in the same container where we're trying to do one thing, we can actually have what we call competing reactions. All it means is they're going to try to stabilize, and they don't care how. So the E1 elimination reaction, ready, is always considered to be competing with the S1. Why? Both those reactions happen when you make a carbocation. If the carbocation, that carbon with a positive charge, has a nucleophile right by, it'll grab onto that and do a substitution. Sure. But what if the concentration isn't high enough? If the concentration of nucleophiles aren't enough, the carbon still has to stabilize. So instead, some of them will probably just eliminate and form an alkene. And so it's very common that even though you're trying to do a substitution, a nucleophilic substitution, you may be forming some alkenes as well, because the conditions that make this carbocation make an instability that doesn't care how it's resolved. It'll resolve by grabbing a negative nucleophile, or it'll resolve itself by forming a double bond to an adjacent carbon. Is this too much for you guys? I hope so. Remember, organic chemistry should be memorable as it is terrorizing. Sardine, your bear's crying. Don't look over your shoulder.
No, he loves organic chemistry.
Now, there's something wrong with that bear, I'm telling you. Eugene, you okay? Okay. E1 reactions are almost always happening with some SN1 reactions at the same time. In fact, it's pretty hard to keep it that clean, which is why if you can do synthesis or make biochemical products that are actually clean, people are going to be really, really interested. The pharmaceutics my company made had virtually no byproducts, and everything we made, we'd sold before we finished. So think about that. When you're doing these kind of things, the cleaner you can do the chemistry, the better it is. Bearing in mind, even if you're trying to do an elimination, even if you're trying to do a substitution, almost always you're going to get a mixture of two things. The substituted product, you're also going to get an elimination. Now, the amount of both of those might vary, but you need to be realistic. You can't control it to the extent where none of these form, but what you want to do is optimize the concentration of what you're going to do. And one of the things people don't seem to tell folks in organic is when you've done this reaction, you're probably still going to have to purify your product because there's a bunch of something else in there at the same time. Maybe you wanted to make this alkene. Whoops. But you also looks like you made a bunch of ether as well. What if you just want to make this substitution, SN1? Well, you also made some alkene. So the reality is reactions compete with each other. Why? Because carbon is as heartless as your instructor, and it wants to achieve stability no matter what. Oh, by the way, Dr. Manuel, thank you for the barbecue yesterday. How come you guys didn't go to that barbecue? Didn't he invite you guys? There was no barbecue. Just kidding. Actually, it's warm enough today that you could probably do that. Don't you guys like going outside and having fun? Dr. Francis,
Yeah,
you haven't
the
been
trees
outside?
covered with snow.
Yeah, sure, why not?
It's still snowing. Oh, true.
We still shovel a rink on the river and play hockey
Well,
all winter.
yeah, I don't play hockey outside, so yeah.
Or organic chemistry does a lot of bad things to your brain and to your judgment is what I'm meaning to think. Okay, no questions? Let's take a little look here. Here's what I said. I've written it down. I'm nagging PlayStation, because this is important. Unstable compounds will seek stability. It doesn't matter how. They're incapable of carrying any reaction will do. They will do part of one, part of another. If it needs 4 bonds, it is going to get 4 bonds. How it achieves it could be substitution or it could be elimination, either or. That is a competing reaction. Doesn't matter how, and you expect that you will usually get a mixture of products. Is okay with that? How do you know I'm not lying? I mean, you're not foolish enough to trust me, are you? Oh, good Lord. Yeah, that's easy enough. This is important right here. Excellent exam question, which means I'm going to probably trick you to get you to learn it and never ask you, just to be that guy. What factors influence reactions? In this case, substitution and elimination reactions. Lots of things influence them, for sure. But let's take a look. First of all, their shape or structure. A little tiny aldehyde with just a hydrogen on one side has lots of ways to get in there and react. But a great big bulky molecule, it can often be hard for the incoming group to work its way in to the site of the reaction. So, is it easier to drive through a crowded parking lot with a blindfold or through an empty parking lot? Also, why are you driving with a blindfold? Yeah, don't put down can drive with blindfold on your City of Winnipeg application. They won't like that. It's harder to drive through a crowded space. So a more complex structure, it will have less reactivity. The nature of the nucleophile or the base. Is it a super strong anion? Is it stable by itself? Is it seeking out any positive charge no matter what? So the quantity of electronegativity, of negative concentration in there is going to have an influence. Oh yeah. Are you doing this in air? Are you literally throwing molecules across the benchtop at each other? Because that's crazy. Don't do that. I suspect you're doing your reactions in an appropriate solvent. And the solvents themselves contribute to reactions. And a little bit further in, not today, I'm going to talk about solvents because that's the thing people don't look at all the time. It's ridiculous. So when you pick a solvent, the solvent might donate protons. The solvent might donate electrons. The solvent might pull away electrons. There's a whole bunch of factors to be considered because I just can't imagine that you're doing your reactions in air. Dr. Salazar, you wouldn't do your reactions in the open air, would you? Just sort of shake them together? Yeah, we don't handle our chemicals like that. The concentrations. This is a big one, folks. All reactions, organic chemistry, inorganic chemistry, biochemistry, all require intermolecular collisions. If there are no collisions, there is no reaction. Number one way to ensure collisions, have sufficient concentrations. 2 molecules in a beaker are never, ever, 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 ever going to find each other. Several billion molecules in a beaker, some of them are probably going to collide. And that's also why we mix them, to increase intermolecular collisions. So concentrations count. Finally, temperature. The same reason that mixing counts, temperature increases microscopic, invisible intermolecular collisions. If these things don't bump into each other, there is zero chance of a reaction. So concentration, mixing, and temperature are all huge factors. Did you guys not study that before? You must have. What's that? You're still thinking about the barbecue you weren't invited to? No, I wasn't invited either. I'm still angry. All right. Can I do a little more? You guys okay? I'm only asking just to be a nice guy, but I'm going to do any more. Addition reactions, ready? Involve. What do you think they involve? Adding something. Yeah, no. It's like, here's the thing. Organic has this weird fear factor, and when you stop panicking and look at the words, show an addition reaction. I think I'll add something. Yeah, of course. It involves breaking a bond, typically a carbon-carbon double bond, and adding an electrophile. Oh, okay. Look here, double bond, ready? Hook the bond, and we've added some stuff. It is literally that easy. There's almost nothing to this. So, just to go over a little bit with you guys. Substitutions is when you have a leaving group, like water, replaced by a nucleophile. The nucleophile probably has to have strong enough charge. Holly, when you were scheduled to have your hand removed from your face? I know, I'm like that. A nucleophile has to have sufficient charge or nothing's going to happen. It'll just sit there. Elimination. You've got a leaving group that goes, and you replace that unhappy carbocation with a double bond. Finally, addition reactions, two groups are added, replace a missing double bond. The weird part is there's lots of little detailed subvariations in organic chemistry with complex names and scary titles, but you're looking at a whole lot of variations of only a few basic ideas. There'll be some exceptions. As we go through the bulk of the material, I'll start working through some of those as well. But you know what? That ends my intro to my intro, and I think I'm going to leave that there today. It's a fair bit to soak up. Now, do you guys have a class after this? For your homework, I'm suggesting you go into the backyard and barbecue something nice, or go to somebody else's barbecue and eat something nice. It's not that hard a task. Or failing that, lie on the couch and play video games or whatever it is you do. I don't know what you do. I'm going to stop sharing that. Alrighty, folks. My research group is studying the variant Omicron of the COVID. My son happens to work in the wastewater. Just so you're aware, the way this is going down is the rapid tests don't really work. An untrained civilian will never stick a tube up their nose to tickle their brain or to punch themselves in the eye, so they're not doing it right. Secondly, it's a very narrow window for a rapid test based on serotyping to work. The difference between the two tests are this. The rapid tests are using antigens, and that means you have to have sufficient exposed viral RNA to get a positive signal. The concentration of available viral RNA is going to vary hugely during the cycle in the patient. So even if you do it right, you could miss it. I know a family of 5, they tested themselves 5 times. 25 tests, all negative, and they all had COVID. So don't be fooled. It does not really work. The PCR test works every time. The polymerase chain reaction amplifies DNA just like your normal cells do in replication. The way it works is it takes a tiny amount of viral RNA, a nanogram from that swab. It amplifies it 30 million times. When you have a 30 million-fold amplification, you will get a true positive signal. The PCR-based testing works fantastically. They can't keep up with in the province, nor do they want to spend the money to keep up with that testing. It's expensive. So now what they're looking at, ready, are absentee rates in schools. By the way, a whole bunch of kids are unvaxxed. That's not good. And they are looking at the presence of Omicron in the wastewater. It's in the water. Do you guys know that? I know. I thought swimming pools were scary already. However, mostly it's been inactivated according to the stuff I've seen. So if you ever do want to talk Omicron, give me a shout. I said I've been working on this for quite some time. Other than that, I guess I won't see you till next Monday or Tuesday. Have a nice weekend. We're not ready for a midterm yet, are we? Yeah, I got to tell you, I don't look, of all things that are horrible to marking organic is horrible, particularly when people don't count 2 carbons correctly. You guys can't see it, but you have to imagine me here crying. Yeah, it's so please count the carbons. Give me a break. But that won't be happening for some time. And to make sure we're all on the same page, the week before I intend to give it, we're going to talk about it. I'll tell you when it's going to be. We're going to have a review. I want to go through how I structure this kind of test. I will never use multiple guesses. I think that's crazy. It'll be straightforward. It should be no problem, okay? Are you going to have a good weekend?
Yes.
Can't remember last weekend? Okay, I guess you're doing this right. All right, folks. It is never too late to apply for jobs. Those sitting jobs are sitting there for the picking, and I know they like to hire you guys. Okay, just saying. Those F-SWEP jobs with the feds are there, and so is the STEP program for the city of Winnipeg. I talked about both of those in our careers course. Those are good jobs. The feds even hired me, which was probably a big mistake. All right, you guys. Have a charming rest of the afternoon. And if you can't be good, well, just be good-ish. All right. So